Hello all and salam sejahtera. Welcome to SEMM 3033 Finite Element Methods. In this video, I'm going to show you the solution to assignment number 5, question 11. Okay, so on your screen right now, what we have here is the solution, not the solution, the answers for question 11. So what I'm going to do here is to solve this problem using Ansys finite element analysis software. Okay, so this is a practice for me because I am not familiar with Ansys finite element analysis software. Before this, I am a user of Abacus FEA software. I've been using Abacus FEA software since the year 2000, about 20 years. But because of this class, what I'm going to do is to make myself familiar with Ansys. One of the reasons is that Ansys Student Edition has more nodal points that can be used for student editions. Abacus can only support, can only give you 1,000 node points, which is not as good as Ansys Student Edition FEA software. Okay, so let's start with this analysis. So if you look at this question here, every information is already given. For example, we have the material property, which is Young's modulus equal to 200 gigapascal. The moment of inertia, which is this number. And of course, part A, part B, okay, part A, part B, you can answer that. Part C is find the unknown degrees of freedom. So in this case, the unknowns are Q2, Q3, Q4, and Q6 because Q1 and Q5 are the boundary condition. So Q1 is roller support, which means there's no vertical displacement. And the same thing with the pin support here, which has no vertical movement, which means Q1 and Q5 equal to 0. And because of this boundary condition, when Q1 equal to 0, we know there's a reaction, which is R1. And then because Q5 is 0, then we have reaction at 0.5, which is R5. So all these are, I think all these have been calculated during the assignment. Uh, and this is my results. These are my results. So we are trying to use Ansys to see if our solution match uh, the Ansys solution. Okay, so let's do the Ansys now. Let's do the Ansys. The first thing that you need to do is to start your workbench. Ansys workbench. I think you should have, if you install it properly, it should be on your menu, and then pick workbench and start it. And what you should see on your screen is something that look like this. So this is your workbench. It says workbench, and we have unsafe project because we just opened this uh, workbench. So what we need to do is to start our project here. So in this case, what we are going to do here is to do analysis. So the analysis that we are trying to do here is this static structural analysis problem. So what you need to do is just click and drag and put it in this box. Okay, for example, when you click, you see there's a green box, and then you just bring it here, and it gives you steps here. It gives you a box, A box here, and then you see that there are 7 steps. 1, 2, 3, 4, 5, 6, 7. So this is what you need to do. You need to follow all these steps. So I want to give this a name. Okay, so my project name is assign assignment number 5 Q11 question 11. So let us save the project, and of course it will ask you where to save your project. So in this case, I'm going to save this in our class. So this is assignment, and I'm going to write a new folder, Ansys solution. Ansys solution to our assignments. Ansys solution. So the project name is, I want to make it the same name as the project name. These are the project files. So assign 5 Q11, and let's just save this. Okay. So this is the first step. So we have defined our what kind of project we are going to do. And then the next thing is to give the engineering data. So if you click this, double click this, it'll give you all the material properties. In this case, this is the engineering data. This is the engineering data. So if you look at this, structural steel is automatically open by the software. And if you look at this, the Young's modulus is 200 times, if we change this to gigapascal, it is just 200 gigapascal, which is the same one as our problem, which is this one here, 200 gigapascal. Okay, 200 gigapascal. Okay, in my case, in this case, what I'm going to do is to define a new material. I want to name my new material as assign 5. So what I need to do is just click here, name it as assign 5, and click enter, and it'll give you a new table down here which says that it needs properties, right? It needs properties. So what I'll do here is to define my Young's modulus. So the way I need to do this is just to click isotropic elasticity, because we are assuming our material as elastic, isotropically elastic, which means the elasticity in the x direction, in the y direction, and the z direction are the same. Okay, so we are not going to use any, in this case, at least in our sample problem, using composite material which has different kind of different values of Young's modulus in different direction. So what I need to do is just click isotropic elasticity, drag it to the property box, and release. So if you look at this, it has two boxes highlighted in yellow. So you need to fill in this. So our Young's modulus from the question paper is 200 gigapascal. 200 gigapascal. So just fill in. Let's fill in 200 gigapascal. So 200 e to the power of 9. Okay, and then click the Poisson ratio. So the general Poisson ratio is 0.3. Okay, it is not stated in the question, but this is a very general value, which is 0.3, and enter. So that's it. So we have defined the two values which are needed. Okay, so Young's modulus and Poisson ratio. So once we are done, there's no more yellow highlighted boxes. So what we can do is just close the engineering data. So the next step to do is to do the geometry. So you need to draw your problem. You need to draw your problem. So in our case, our problem is just to draw the line here, which is this line here. This is the beam is represented by lines here, by lines. So how many segment of line do we need here? So let's go back to the workbench, and you can, once you are done with the engineering data, you see that there's a tick mark here, a tick mark. So this one is still need to be defined. So highlight that one, click the geometry, and you can double click, and it will try to open up. Oh, I'm sorry. I think I picked the wrong one. Never mind. I picked the wrong drawing editor. As you can see down here, it says starting space claim. I don't want to do using space claim, but I'm going to use another drawing editor. Okay, so this is, wow, this is something totally new to me. So let's close this one. I'm not going to use this space claim, but let's try to use this one here, which is new design modeler geometry. So this is what I want to use. I want to use design modeler geometry, okay, as my drawing editor, or my uh, what do you call that, graphic editor, or in this case my model editor. So let's do this. Click that, and it will say down here starting design modeler. So you need to wait for a few minutes because my PC is slow. My PC is slow. Okay, I think my modeler is running. So this is my uh, design modeler. This is my design modeler. So if you look at this left hand side, there's XY plane, ZX plane, YZ plane, and parts. So if you look at this, there's nothing. There's nothing here because we have no parts yet. We have no parts. So what we did just now was defining our engineering data. So the next thing to do, according to Workbench, is to draw the geometry, to define the geometry. So let's go to our modeler here. So if you look at this tab here, there's these two tabs here. You see that there's a modeling tab and there's a sketching tab. So let's do sketching. So once you do the sketching, you see this X, Y, and Z direction. So X, Y, Z direction. So since we are drawing only line element, we are drawing a line in XY plane. So if you want to look from XY plane, you can just click this, and automatically you have only X and Y. So Z, Z is going out of the uh, plane. So I would like to do some settings here. So the first thing, I need to turn on my grid, and then I need to use my snap, and then the rest I will leave it as it is. I don't want to do that. I don't want to change. I just let it be like the default value. So let me draw. Let me draw the lines here. Let me draw the line. So now, how many line segment do we need to draw here? So if you look at the question, here, what we can see is that this is our boundary. So that's one point of interest here. There's another one point of interest here, and one in the middle, which is where we apply the concentrated load going downward. So it is a good idea to define two lines. One line is for this one, this segment here. The other line is from here to here. So basically one line for A, B, and the other line is for B and C. Okay, because we need to apply 15 kilonewton concentrated load going downward at point B. So let me draw the lines. So just click line. Okay, so I click this point here, and I click this point here. Okay, another line. So I just click line, and then when we are done, you need to generate. So the line is there, and if you see this is too small, so why don't we zoom in? Okay, this is our zoom to fit. So these are, we cannot see the lines here. So the next thing to do is to give it the correct distance, or sorry, the correct dimension. So you can just go to dimension and then general dimension. So just click the first line. So this is the first line. Okay, so H1, and this is the second line, and you can see that our H1 line, H1 and H2 dimension are given down here at this box here, detail view. So we know it is not supposed to be 4 meter, but it is supposed to be 5 meters. Okay, 5 meters here, 5. So we need to change this value here. We need to change the value. So what we'll do here is just change this to 5 and to 5. So automatically the drawing will be updated. Automatically the line will be updated. So let's zoom in. Okay, let's zoom. So these are the two lines. So this is one grid, one box here is 1 meter. So 1, 2, 3, 4, 5. So these are the dimensions now. So we are done. With that. So let's generate the lines. Okay, so what we have is just a sketch. We do not have the actual line yet. So what do we need to do? So we need to generate the line. So how do we do that? So on this menu here, you have the concept. So what you want to do is to generate lines from the sketch. We sketched 2 lines, but it is not a line yet, it's just a sketch. So we sketch, we change the dimension. So once we are sure, then we can generate the line from the sketches. So just click this. Or before that, let's see what is the modeling part here. So this is the modeling. What you can see here, we have sketch 1 on XY plane and nothing else. We just have the sketch. So what you need to do is just, it says here, this is the sketch. So we can generate the line from our sketch. So concept, generate lines from sketches. So now what we have is this one here. So this is the line. So you see there's this flash sign here next to this line. So which means we need to generate this. So click this and generate. Okay. So before that, you need to select which are the lines. So in this case, click line. It says here object not selected. This object is not selected. So what we can do here is either you select this, and let's try to do that again. Okay, so what are the base objects? So this is one, and okay. Oh, you need to use, you need to hold control and click the other one, so it will add up. So there are 2 edges here. So apply. It says one sketch. So we have, now we have the sketches. Now what I need to do is, because there's a mistake here, what I can do here is just to, okay, now we have generated the sketch. Okay, I'm trying to delete this. Okay, so yes, now we have the sketch. Okay, we have the sketch. Now we have the line from sketch 1. Okay, and we have a line body here. We have a line body, but this is this has no section. This has no section because this is just a line element, right? So, but for beam problem, we need to define the section. We need to define the section when, because we have our I, we have our I, the moment of inertia. So we need to define the cross section. So what is our I here? What is our I? So let's look at this question. It says I is 100 times 10 to the power of 6 millimeter to the fourth. Millimeter to the fourth. So how do we define that? How do we define that here? Okay, without cross section, we cannot define this. We cannot define the uh, I. We cannot define I. So how do we define I here? So we need to define, the first thing we need to define what kind of cross section of our beam here. So let's go to concept and let's go to cross section. So cross section. So there are a lot of cross section here. So we can also define our own. Oops, this is not the one that we want. So let me delete this. Okay, we do not want that. So we need to go back to the concept, cross section. So the easiest one is rectangle. I use rectangular, or you can also use this one, user integrated, where if you look at user integrated, you need to fill in all this value, or at least some of the values. So you need to know what is IXX. So in this case, we know our IXX, we know our IYY. Okay, what we do not know what is our J here. So I'll do some trick here. So let me delete this one and let's define uh, our our cross section as a rectangular. Okay, so this is our rectangular area. So what do we need here? Okay, what we need is to make sure that our IXX is the same as the one in our question, which is 100 times 10 to the minus 4, sorry, 10 to the minus 6 millimeter to the power of 4. So we need to define that. So before that, if you look at this, you look at the screen here, I have my rectangular, I have my square here, or I have my rectangle here, but it is out of proportion. Let's move this dimension somewhere here. So what I can do, either you can click here, right click and move dimension, or you can also click here and move dimension. Okay, so what I'll do here is I just drag this up to here, and I also can drag this up to here. Okay, and then I can zoom. Okay, so this is my cross section. So in this case, I'm using a square. I'm using a square uh, cross section. So I need to define my base, my B and H in such a way that my IXX is equal to the value in our question, which is this one here, which is this one here, which is this one. Okay, so how do I do that? How do I do that? So the way I'm going to do this is that this way. So we know that for our rectangle, I is just 1 over 12 BH cube must equal to 100 times 10 to the power of 6 millimeter to the power of 4. Okay, so since our B and our H are equal, okay, because we are using square, so our B and H are equal. So this is a square. So now this is 1 over 12 B to the power of 4 equal to 10 to the minus 6 meter to the power of 4. Okay, so B4 equal to 100, 1 times 10 to the minus 4 times 12, and we have to find the cube root. B is equal to this value here, okay, times 12. So if you do this correctly, what you get is, what you get here is 0.186, 0.186, 12097. Okay, at least this is the workaround that I'm doing here. I don't know if there's a better way. At least for now, I do not know a better way to do this. But if you discover a better way, or if you have more if you are more familiar with Ansys than I am, so maybe you can tell me how to do this efficiently. So now let's define our B. Okay, let's define our B. Okay, so what is our B? Our B is 0.18612. So let's define our B here. So it is 0.18612.097. So let's copy this. Let's copy this. So I can use it for down here. Okay, now I have the two value B and H. B and H are equal. Now look at our IXX here, which is 1 to the minus 4 meter to the power of 4. So we get the correct value. Okay, because this is a square, our IYY is equivalent to our equal to our IXX. So we are done with this. We are done with this. So the next thing to do is to give this cross-section area to this body here, to this body. So look at this. It says cross-section. It's not defined yet because it is still highlighted in yellow. So what we need to do is to assign. Okay, so the assignment, this is none. If you scroll down, it says rectangle 1, rect 1. So hit enter. So now everything, there's no yellow highlight anymore. So there's no yellow highlight here. There's no yellow highlight here. Everything is clear now. Everything is clear. So now what we have done is we have completed our model. We have completed our model. Okay, we have completed our model. So we have defined our geometry. We have defined our geometry. It's a line, it's two segment line problem with a rectangular, or in this case, a square cross section. So we can, I think there's a way to view this section here. So let's zoom out a little bit. And if you go to view, then we have cross section solid. You want to see the cross section. So this is the one. So you can, of course, you can rotate this. So you can see the shape here. You can see the shape. Okay, you can see the shape. Okay, you can see there's a rectangular. Zoom in a little bit. You see that this part here is square, and this is the total length of the line. Okay, note that this is just the cross section area. It's not this. It has the line has no thickness. The line has no thickness. This is just for the sake of calculating the I, the moment of inertia. So I think we are done here. We are done with our model here. We are done with our model. So our model is a line with rectangular, or in this case, square cross section area. So we are done with that. So we can just close this. We can just close this. Now, since we are done with the geometry, we need to go back to our workbench. So now we are done with the geometry. If you can see that the geometry has been ticked. So engineering data is done, geometry is done. So next to do is the model. Look at this. We have to do all this model here. So this is step A4. Step A4. So let me right click and just edit. Okay, right click and edit. Or you can just double click and it'll give you, it will take a while. It will take a while. Okay. My uh, my modeler is on now. Okay, so if you look at this uh, workbench, so my model is under there's a flash sign here. Basically, it is need to be it has run, but we need to uh, model it. We need to give all the properties, and then we can once we are done with that, we can continue with the rest of the steps. So if you look at my mechanical modeler here, it says here A4, okay, which correspond to this workbench. Step A4, we have step A5 and steps A6 here in one modeler here, in one modeler. So if you look at this is my this is our line just now. This is our two lines for our model. These are the two lines, and it has no cross section. It has no cross section. It's not displaying the cross section. So what we can do here is just go to this tab here, this tab display tab, and you can click this cross section. It will give you this. It will give you the cross section of the beam here, of the beam. Okay, so let's go and take a look at all this thing here, all these three here. So we have the geometry, which is a line body. Okay, it's just a line, but because of the cross section, it's drawing the cross section for you. And the material, okay, so I have assignment 5 material just now, but it is not being assigned to this model yet. It's not been assigned. So maybe we can do that later. So I don't want to see this. We can close this because we do not need to see this. Okay, so the cross section, we have rectangle 1. Okay, rectangle 1. If you click here, it says all the properties that we need, which is our IYY, our area, our base and height dimensions. Okay, and then the coordinate system, and there's a mesh here. If you look at the mesh, you see that there's a flash sign here, which means it is not yet generated. It is not yet generated. So let's do the mesh. So if you click here, okay, so what I'll do here is what I want is to insert the sizing here, the sizing. Okay, actually you can also see that there's a sizing down here. Okay, you can change the sizing if you want. Okay, so what I'll do here, I just put it here, so I don't need to go down here. So just right click, insert sizing. Okay, insert sizing. Note that in this case, there are two yellow boxes here. So what are the geometry and what are the element size? Okay, what are the element size? So let's pick the geometry here. So let's pick one of these. And okay, maybe we can turn off the cross section because you cannot see. Hopefully you can see my green line. It is too thin here. Control, hit control and click. So these two are selected. And then you click here and then apply the two selection. So now we have the lines here. Or maybe now I can draw the cross section. And then the how are we going to size the element? Okay, so we know that one line is 5 meter, the other line is also 5 meters. So we can either define the size or we can also define the number of division. So let's say for each element, we want to have only one division, only one division. So here number of division is 1, which means there's one element here. For the first line, there's one element for the second line, which is the same thing as what we did for our assignment, which is a 2-element problem. So now what we need to do once we are done with that, there's a tick sign which is okay, but we still need to generate the mesh. So just right click and generate mesh. Generate the mesh. And now you can see the mesh. So this is one mesh, one element. This is another element. So you can see here, hopefully you can see there's a division line here. So maybe I can zoom. So this is the boundary between first element and the other element. Okay, the other element. So we can zoom back to this one. Okay, so let's do this way. So I have 1 and 1. So we are done. We are done with the sizing of the uh, mesh. So in this case, we have 2 elements for our problem. Next, it's if you look at this, it says here, this is our structure, static structure problem. So let's look at uh, our workbench. So A5 is basically setting up the problem, setting up the problem. So what does it mean when it says setting up? So we need to define the boundary condition. We need to define the loadings for this problem here, So what I'll do is right click on the structural. Okay, and before that, I need to do something else here. For the solution, we still haven't defined our material yet, right? So I keep forgetting to define our material. Where is our material? Uh, okay, okay, beam section. Let me try to find the mesh sizing. Okay, this analysis setting, nothing. The solution setting. Okay, uh, I know I need to define my material, but I think I have forgotten where I defined it last time. So never mind. Let's go back to the material assignment uh, when we find it. Unfortunately, we cannot find it now. Meters, body, properties. Yeah, under properties. Not there. Okay. I think I've forgotten where to define it. Never mind. Material assignment. There are 2, but we have not yet assigned the material yet. Okay. So model. Geometry. Never mind. Never mind. Let's do that later. Uh, I'm confused now. Where should I define my material? Never mind. Let's set up the problem. So what we need to do is to define our boundary condition first, or you can apply your forces first. In my case, I like to do my boundary condition. So let's look at this one first. Let's look at the question here. So how do we define the boundary condition? So when we solve this using our manually, you know that the boundary condition is only Q1 and Q5 equal to 0. But when we are doing finite element, we need to, I think, to give more details to this, to the software. So in this case, when we have the load, what we can see is that the beam will deflect, something like this, and there's a pin joint here. There's a pin joint. You know, for pin joint, there's no, because it is fixed, there's no delta x. It cannot move in the x direction. It cannot move in the y direction, which means this is equal to 0, and delta z, of course, out of plane is equal to 0. But if you look at this, because of this, there's a angle, which means there's a rotation. There's a rotation. Because of rotation, there's a moment there. There's a moment. Moment is not 0 there. Okay. There's there's a rotation, which means there's a rotation there. Okay. So rotation is not equal to 0. So delta or rotation here is not equal to 0. Okay, the same thing for the roller side. For the roller side, we know that there's delta x is not equal to 0 because it can displace in the x direction, but our delta y will become 0, and rotation here again is not equal to 0. So theta is not equal to 0. Okay, because the beam deflects. The beam deflects. So we need to define that in our software. So let's do that. Let's do that now. Let's do that and right click, insert. See, you have all these options here. So what I'll do here is I want to define my remote displacement. Okay, it says here is set a remote displacement object to apply both displacement and rotation. If we just use this, it only says insert displacement boundary condition, but it didn't say anything about the rotation. Fixed support is, again, boundary condition prevent a selected geometry or mesh entity from moving or deforming. So which means not only the displacement, but also the rotation is being restricted. So let's insert this. I'm using remote displacement. And you see here is that X, you see the yellow boxes here, X component, Y component, Z component are all free to move. Rotation X, rotation Y, rotation Z direction are also free to move. So I need to select a point. So what is the geometry? So I need to pick this point here, this node. So I click here and I say apply. So one vertex. So remote displacement. So I know for movement in the X direction, it should be 0. Movement in Y direction, it should also be 0. Okay. And in the Z direction is also equal to 0. So there's no rotation in X direction. Okay, no rotation in Y direction. But there's rotation in Z axis, which is free to move. So when I'm done here, it says here component, this is displacement X, Y, and Z are equal to 0. Rotation in X axis is 0. In Y axis is 0. But in Z axis is free. And this coordinate is X 10, Y 0, because this is my origin here. 0, 0, 0, 5, 0, and 10, 0. 10 and 0. So I'm done with this boundary condition on this side, on the right hand side. So let me rename this as pin join. Pin join. Okay, so the other boundary condition is on the right hand side, which is my roller. So there's a roller here. So let me add insert another remote displacement. Okay, remote displacement. So X is free to move. Oh, okay, before that, let's select my point. So this is the point here. This is the point. And apply. Okay, so the coordinate is 0, 0, 0, which is my origin. So x is free to move, but y is not. Oh, y is not. Okay, z is also not free to move. Rotation in x-axis is also not. Rotation in y-axis is also not. But rotation in the z-axis is free to move. Free to move. So I'm done here. So it's telling us now, before that, let's rename this as roller support. Roller support. Okay, so this is roller support. And the other side here is the pin joint. Pin joint. Okay, if you want to see what I have done, you just click structural analysis. Static structure, it say point A is my roller support, point B is my pin joint. It's my pin joint. Okay, so we are done with the boundary condition. Now let's define the forces. Let's define the forces. So we have one force here. We have 15 kilonewton going downward at point B. Okay, and then we have distributed load from B to C, and then we have moment at point A. Okay, those are the three loads. Those are the three loads. So let's define our loading now. Let's define our loading. So insert first the force. Okay, where are the force? The force is going to be applied here. Okay, so how do I click my point? So let's do this. Let's use this one. Let's control this to vertex. Click this. Something's not right here. Let's do this again. Let's do this. Why is it not giving me? Not giving me. Oh, okay. So I think I know why. This is a zoom. This is a zoom. So let's do this. Okay, this should be the one. It seems that my cursor is giving me problem here. Okay, it should be this one. Okay, there. So now apply. So I have a force there. So define by, either you can define it by vector, or you can define this by by giving the components here. Giving the components. So let's define this by components. So in our case, we have no x component, but we have y components, and the value is what was the value? The value is 15 kilonewton. 15 kilonewton. Okay, 15 kilonewton going downward. Going downward. So 15 kilonewton downward is minus 15. Okay, e to the power of 3, which is kilonewton. Okay, so hit enter. So you can see that my force is going downward, and the value is 15 kilonewton. So if you go back to here, you see that we have defined our two boundary condition, we have defined our force, and let's do the next force, which is the distributed load. Okay, insert line pressure. Line pressure. Okay, click this, and line pressure is applied here. Right, it's applied along this line here for this element. So click the element. I'll say it's highlighted as green, and click apply. Click apply, and then define the force. I'm using to use components, and now it's again going downward. Okay, which is a minus, and I think the value should be, if I'm not mistaken, 5 kilonewton per meter. 5 kilonewton per meter. So it's minus 5 kilonewton. 5e to power of 3. 5 kilonewton. So it's going downward. And let's go back. So we have two loads, we have two boundary conditions. We still need one more, which is the moment, here, which is 80 kilonewton meter. 80 kilonewton meter. So our line pressure is 5 kilonewton per meter, which is okay. Now we need to define here our moment. So just right click and insert, right click, insert moment here, moment. Okay, moment. So okay, so if you look at the icon here, positive direction is counterclockwise. So let's pick the point. The point is, let's use this one. Okay, the point here. Okay, apply. And again, let's use this component instead of vector. So in our case, our moment is in the z direction, z-axis. So z-axis of 80. What's the value? Forget. Which is 80 kilonewton. 80 kilonewton. So 80 e to the power of 3 kilonewton. Okay, and hit enter. And note that the direction is wrong. Our direction should be clockwise. So that we need to change it here. We should put a minus sign. So now this is in the right direction. So let's look at this. So we have three loads. We have force, we have moment, and we have line pressure. And then we have the boundary condition, which is roller support and pin joint. So we are done. We are done setting up the problem here. So let's look at A6. What is A6? If you go back to our workbench, 6 is the solution. Okay, 6 is the solution. Note that our setup and solution is still having the flash sign, which means we are not done yet. We did not do anything yet. So let's go back to our modeler here. And the solution here. So what do we want? What do we want in our solution? Okay, I'm still worried because I haven't defined my properties yet. Where is my property? It should be here. Material property, yes. Okay. I don't know where we should put our material properties. Okay, we do not need this one. Cross section. Okay. Coordinate system. Okay, Cartesian. Mesh. Okay. I'm a bit worried now because I cannot find where to define my material properties. Yeah. Okay. Okay, this is nothing. Okay. All right. I still cannot find where's my material. Yeah. Never mind. Never mind. Let's put that on hold for a while. Okay. So in this case, what do we need for our solution here? What do we need? Okay. The one that we need is at least the the deformation, right? So we need to find the directional, which is in this case we need to find the deformation in the in the y direction, because there's a deflection there. There's a deflection. Okay, so I think that's it. That's it that we can uh, at least one of those. Okay, we can find. Let's try with one of these. Okay, let's see. Let's try to find the deflection first. Okay, the deflection. Uh, okay, so let's okay, either we can do the analysis now, or we can add more solution that what we want. Okay, for example, in this problem, we need to find the reaction, right? We need to find the reaction. We need to find the reaction. Okay, so find the reaction. So we need to find R1 and R5. R1 and R5. Okay, we need to find R1 and R5. So we can put that later, or we can put it now if you want to. So let's say insert uh, uh, deformation bolt probe force reaction. Yeah, force reaction. Force reaction. At what point? So at pin joint. Okay, at the pin joint. Okay, at the pin joint. So that's one force reaction. So I can rename this force reaction at pin joint. Okay, then I can have one more force reaction. Okay, insert force reaction. Okay, which is at the roller support. So I rename this at roller support. At roller support. Okay, so we can add more later before we run this problem. Okay, we can add more later when we want to do that. Let's do this. Okay, so I can see more. Okay, so we are almost done there. We are almost done, except we have not defined our material properties. Okay, except we have not defined our material properties. Okay, so why not let's try and see what happened. Let's try and see what happened. Okay, so what you need to do is, since there's a flash sign here, you need to click uh, click I'm still worried about my properties. Where is my properties? Okay, never mind. Just let's try this and see what it should give us an error message if we forgot to define our material properties. Okay, it gives us some warning here. Okay, no error messages. No error messages. Okay, no error messages. I still worried, where did I define my material properties? Okay, advanced geometry option. Come on, man. Where is my properties here? Okay, never mind. Never mind. Okay, let's see the results here. So what is the directional deformation? Okay, this is only two elements, right? So we need to find, in this case, what is this value here? What is this value here, which is the deflection at point B? Okay, there are ways to do this. You can see the results. Okay, and then you can use probe and just move your cursor, your mouse to that location. And in this case, let me click this, and it's giving me 53.67 millimeter. 53.67 millimeter. And compare that to our solution, which is our Q3, minus 56.902. Okay. Almost. Very close. Very close, yeah? Very close. So for the deflection, I know how to find it. But for Q2, Q4, and Q6, which are the rotation in radian, unfortunately, I do not know how to extract the information. Because in our solution here, when we are trying to insert, there's no selection there. Okay, I know in Abacus, we can find the deflection, but not in Ansys. At least I do not know how to do that right now. Maybe if you know, please let me know, or I need to read the manual how to find this deformation. So this is what I get, minus 53.67 millimeter. Okay, now what about the force at the pin joint? Okay, force at the pin joint is this value here, and it is 34.25 kilonewton. 34.25 kilonewton, which is R5, and the value is the same, 34 point, is it 34.25 kilonewton? Did I get that one right? Okay, or did I copy the wrong solution? Let's look at R1. R1 is at roller support. Roller support is 5.750 kilonewton, which should be the same. Okay, so R5 is wrong. R5 is wrong. R5 is wrong. It should be 3,425. Okay, so maybe that is the issue here. Maybe that's the issue here. So let's double check where we did wrong. Okay, let's double check where we did wrong. Okay, I have double checked my solution. Actually, it is correct. It is correct. So what I did was, when I copied the solution, I put this decimal place wrong. It should be 34.250 kilonewton, which is the same solution as our finite element software, solution. So now that we know our displacement and our reaction are correct, so what are the other information that we need to find? Oh, we need to find our moment and our shear at midpoint of B and C. So the solution is already given here as 64.794 kilonewton meter and 21.75 kilonewton for the shear. So let's do that for our finite element model. So if you look at this, so we need to add shear. Okay, so insert, we need to put shear force. Okay, shear force. We do not want total shear force, but what we want is only directional shear force, which is directional in the y-axis. So let me rename this. Oh, okay. It was already given. It's already written here, directional shear force. Okay. So the geometry is all line body. And the next thing is to add the insert mm, ooh, moment, bending moment at midpoint of B and C. And again, this is also directional, and it should be moment in the z-axis. So z-axis, and we are done. So let's generate this two solutions here. So right click and evaluate our results. Evaluate our results. Okay, we are done. So let's go to directional shear force. So the shear force, okay, because there are shear force is not location based, it is element based. So shear force in this element and shear force in this element. So let's probe the value. So the value is 21750, 21750. So in this element, it is 21,000 point 21.75 kilonewton, 21.75 kilonewton. So let's click that, uh, and let's click that. So these are the value for this element, which is part B and C. So what is the value? The value, the results is 21750 Newton, which is the same as our solution, Okay, now let's go to the bending moment, And okay, unfortunately, bending moment is based on node point. So there's no node point here in between B and C. So we need to find moment at this location, right? But midpoint of B and C. But unfortunately, there's no nodes here. The only node is in the center, on the left edge, the center, and the right edge. So there's no moment at this. There's no point at this location. There's no nodes here. So what we can do is just to maybe take the average. Okay, take the average, which is in this case, this is 10 to the power of minus 9, which is very, very small. And this is about 10 to the power of 5, which is very, very huge. So in this case, using two elements is not sufficient to evaluate our moment at this location here, So what do we need to do? We can increase the number of element, right? We can increase the number of element. So in this case, what we can do is we go back to the sizing. And instead of using two edges, instead of using only one element, uh, one division for each element, now let's try to increase this to 2, so that we have 2 here and another 2 here. So let's generate this. Let's generate mesh. So now we have this node, which is the center, the midpoint of B and C. So let's regenerate this. Note that there's a flash sign, which means you need to generate. Okay, you solve this, and okay, it's calculating here. Okay, now we are done. So let's look at the directional bending moment at this node here. So let's use the probe, and it says 70 kilonewton meter. 70 kilonewton meter of bending moment. So our solution is 64.795 4, okay, which is not that close. So what if we increase more elements? Okay, let's increase more elements here. So edge sizing, okay, number of division, hmm, let's say 11 on each of the, oh sorry, maybe 10. Let's try with 10 first on each of the division. Yeah? So we have 10 here and 10 here. And let's solve this. Okay. Okay, let's look at the bending moment here. So we are interested at mid of BC, which is this location here. Still the same number, 7T, 7T, which is 70, yeah, which is 70 kilonewton meter. 70 kilonewton meter. So I don't know why I didn't get the right answer, because I think I did this before and I get almost the same solution as the one I did it, which I did manually. Okay, so never mind. Uh, Never mind. So at least we know we got our shear correct. We got our reaction correct. We have our deflection almost correct. Oh, let's see our deflection now with more elements and see what is the value at this point. Minus 56.899 millimeter. And the solution is minus 56.9, okay, which is very close now to our uh, two element solution. Two element solution. How about our reaction? Reaction is still the same. Okay, still the same. What about our shear force? What about our shear force? Okay, we probe this. Okay, note that this is not the midpoint. So there's four. This is the point. So we need to take the average. This is 23K, 23.5, 23 kilonewton. Okay, and the solution, our hands-on solution is 21. 21, right? 21. So again, this is not as accurate because we are only just using two elements, right? So let's add that. We can add more elements if we want to. So let's change this. Maybe we say, let's increase this to maybe 50 division for each. And let's solve this. Okay, let's solve this. Okay, we are done. We are done. So let's look at the directional deformation. And let's look at, okay, we can animate this if you want. Okay. Okay, let's stop that. And we can also change the contour. Let's use smooth contour. And let's use no wireframe. Okay, and let's animate this. So let's animate this. Okay, so we can stop that. And we need to find our displacement. Okay, sorry, let's go to result and let's probe. What is wrong here? Okay, it takes some time. So it is, I don't know which node is this. It says the node is location. Okay, this is X. X, uh, X is 5. So which is, this is our center node. Okay, 5. And the deflection is minus 56.9 millimeter. 6.9 millimeter. Okay, so we can also look at our bending moment at somewhere here. Okay, it is 74.250, 72, which is 64 something. So again, it is getting more accurate as we move on. Okay, so I don't know how to look at this. Let's try this. Is this the bending moment? So what node is this? Results and location is 7.9. We are interested at 7.5, which is somewhere here. 7.8, maybe somewhere here. 7.6, maybe from here. 7.5. So the result is 70K. 70K. So no change. No change. It's the same thing as we use uh, more elements here, more elements. Okay, so I think that's it for our demo here, for our demo. I don't remember where I defined my material. Maybe I have defined it before, but maybe I've forgotten that I have defined it. Okay, so uh, let's pause for a while until I can find where I define my uh, properties, material properties. Okay, so I'm going to pause the video for a while and let me try to remember where I define my property. Okay, I think I know where to define this material property just now. Okay, so what we did earlier was we went to our workbench, right? We went to our workbench and then we go to engineering data and we define a new material which is assign 5. And for assign 5, okay, the Young's modulus is as given in the question paper and our Poisson ratio is 0.3, which is the general value that we use if you do not know what is the Poisson ratio. So we are done with that. And then the next step is to go to our geometry, we draw everything, and then we go to our model. So let's go to our model and edit this. Okay, so we managed to run this problem here. We need to run the problem, but uh, fortunately, the Young's modulus for this problem is the same as the one in this question. So if I really need to change my material properties, I need to go to geometry, line body, and when I click line body, part of this table down here is saying that material. So my material is structural steel. Fortunately, structural steel is the same, has the same Young's modulus as our assigned 5 Young's modulus. So I can change this to assign 5, which is now the value that I want, So if you change this new material, you see that the static structural analysis has the flash sign and the solution has also the flash sign. So it means that you need to solve. So let's solve this. And okay, let's wait for a few minutes, a few seconds. Building mathematical model. Okay, solving the mathematical model. And should be done now. Should be done. So since the Young's modulus value is the same, there's no change in result. Okay, directional deformation is still the same. In this case, which is uh, uh, 5.7 because we have more elements now. So let's change this to maybe not as many division. Maybe let's try to use 2 divisions, and let's generate. Okay. Okay, now we can have the results now. Can have the result, which is 5.61. Okay, 5.61. Okay, of course, this is not as accurate because this is only using 4 elements. Okay, so I hope this video will at least uh, help you start uh, trying or start familiarizing yourself with Ansys software. Okay, even though I'm not that familiar with Ansys, at least I managed to do the problem. I managed to do the assignment problem and solve it correctly and solve it correctly. Okay, so I think that's it for my video. Maybe next video I will do the other problem, which is the frame structure. Okay, I think it's in assignment 6. Okay, maybe I'll try to do that later, and hopefully we can get the same result as the uh, solution that we get for our assignment. Okay, until we meet in another video. That's it for today. For now, thank you very much.